In the following presentation, I, Victor Fernandez-Ayala, will present the publication titled Distributed Barrel Function-Enabled Human-in-the-Loop Control for Multi-Robot Systems, submitted to ICRA 2023. The main background element for this work are control barrel functions. Essentially, they are a tool that allows us to ensure specific properties for our system. The idea is that we establish a safety set C, which is defined as the region of the problem space where a custom function h is greater or equal than 0. And by using the CBF condition, shown in the equation below, as a constraint, we can ensure that the system will always remain inside this safety set. More specifically, if U is locally elliptic, this condition will render the set forward invariant, meaning if we are inside the set, we will never go out. And if C is compact, it is also asymptotically stable, which means that if we are outside of the set in the unsafe region, the system will asymptotically converge towards the inside of the set, that is, the safe region. Originally, this constraint will be simplified as a linear condition with coefficients a and b, and it will be solved as a centralized optimization problem. The safety constraints that have been considered for this work are the following: arena size, which makes sure that the agents always remain inside of the workspace; internal obstacles, which are represented as circles, and the CBF function is the distance between the obstacles and each of the agents. Then we have connective maintenance to keep all of the agents close together, intercollision avoidance, which is the opposite in order to try to avoid these collisions between agents, and lastly, collision avoidance with the extra robot or human. With this, we create our CBF-enabled mixer, which takes human commands, existing multi-robot coordination protocols, and the safety constraints, and create safe commands for the multi-robot system. In this first experiment, the centralized algorithm is shown for two different settings, both using a multi-agent system composed by 4 robotic agents with a nominal controller keeping them in a square formation. The one in the left shows mixed control with human commands, where human inputs are sent with a handheld controller, and the optimization objective minimize the norm between the output U and the human commands subject to the safety constraints. The one in the right shows what happens when a human enters the arena and a collision avoidance constraint between robots and the human is added to the optimization problem, allowing the human to safely hurt the multi-agent system. In the following plots, the evolution of the CBF functions h for each constraint are shown. That is, for arena walls, communication maintenance, intercollision avoidance, and avoidance with an internal obstacle for both of the cases previously shown. The next step in this work is to create a distributed implementation of this algorithm. This is based on previous work done by one of the authors. Just to quickly summarize this result, the following equivalent QPs are solved by each of the agents where only local information is used. Additionally, a new auxiliary decision variable y is created that is also added into the set of information. If all the equivalent local QPs are feasible, then the new distributed problem is the same as fulfilling the CBF condition for the centralized case. The question now is to obtain the optimal value for the auxiliary variable y. To achieve this, the extra variable c is created such that if all the c's are the same, then y is optimal. So using the following discontinuous adaptative law ensures that C will reach consensus in finite time, and therefore the optimal solution for the QP is found. This result originally only allowed one collective constraint, so in this work we extended it to several by grouping together all the constraints into one with the minimum operator, and enforcing that it must be greater than 0. Additionally, the logarithmic approximation of the minimum function was used to adapt it to the previous formulation. In this second experiment, we saw the same setup as for the centralized algorithm, but with our new distributed one. This means we have the multi-agent system composed by 4 robotic agents with a nominal controller keeping them in a square formation. The one in the left shows again mixed control with human commands, and the one in the right shows formation control with an extra human in the arena. As you can see, the behavior is quite similar to the centralized one, and it fulfills all the safety criteria, although it behaves with a bit more jerkiness. This is due to the delay introduced by the communication link between agents when solving the distributed optimization problem. As before, we also saw the plots of the evolution of the CBF functions for each constraint. In the left, some for the mix control with human commands, and in the right for the formation with the extra human in the arena. All the plots show that the safety constraints are always satisfied since the evolution of H is always negative. With this, I conclude this presentation. Thank you for listening. If you have any questions or further inquiries, feel free to email any of the authors at our emails at KTH.